Good morning, ladies and gentlemen. Welcome to this video on trig derivatives. Before we get into derivatives, let's just remind ourselves what the trig graphs look like. Sine and cosine look a lot like each other, just with a translation involved, and tan is completely different. It might help us to remember that when the sine graph is 0, say at 2 pi, the tan graph will also be 0. It's because the sine graph is on top, cos is on the bottom, so when cos hits 0 at, say, -3 on 2 pi, tan will asymptote. And that's what gives us this very strange looking tan graph. Alright, in terms of the derivatives, the proof for the derivatives, you're welcome to look up. Or in the book. The book one's not so good, so Google the proof if you're interested. But I think the best way to sort of visualize how the derivatives work is to look at a graph of all of these functions. So what you're looking at here is the sine curve, and that red arrow is the instantaneous slope of the tangent. So right now, the slope of the tangent is 0, and what you might notice is that there's a little red dot and 0. That red dot is going to track the value of the tangent. So if I drag it here, you see how the tangent goes positive, and at this point, the tangent is the steepest it's going to be. It is steeply positive. In fact, its slope is 1. As I go beyond that, the slope is still positive, it's just not as positive as previously, until I reach this peak, and the slope, or the instantaneous gradient of the tangent, is 0. And then we head back down. Now the slope's negative. It's getting increasingly steeply negative until we reach this point. At this point, it is a slope of -1. And we continue like this until we get back to 0. And what you might notice is that the slope of the tangent follows exactly the same pattern as the sine curve. It's just translated over. And that translated over turns it into the cosine curve. So what we're looking at here in this red and blue line is the cosine curve. So what this allows us to say is that the derivative of the sine function, I don't want to show you the rest just yet, the derivative of the sine function is the cos function. So when you derive sine x, you get cos x, which is really neat. It's really simple. What about the other way around? What about if we derive cos x? Well, it's not quite as easy. Alright, so we're looking at cos x. Same deal, we drag this, and we get something that looks very similar. Let me just zoom out. Oh, we can't quite zoom out. Zooming out's not going to work. Cool. This curve here is similar to the sine curve, but it's not quite the same. So note how it goes through the center like the sine curve does, but then after it goes through the origin, it doesn't go up. Ooh, you can zoom in. Where'd our little thing go? Restart. So after the origin, anyway, it doesn't go up, it goes down. So if you look at the sine curve up here, this black one, at the origin it goes up, but down here the derivative function heads down. It turns out that the derivative of the cos is just the negative of the sine curve. So the derivative of cos is negative sine. Now, just focusing on these two for a second, how are you going to remember it? Well, A, you're going to have it written on a cheat sheet. If it helps you remember it, I think of sine x as simple, sine and simple, kind of similar words, so it stays nice and simple, it just goes to cos. Cos is difficult because it's difficult. It just goes to negative sine. Alright, then tan x, and we're actually going to do a proof in a second because there are a few proofs you need to know, and tan x is one of them. So the derivative of tan x is 1 on cos squared x. Note, 1 on cos squared x is also sec x. There are these three, I guess, alternative functions that you may see pop up. Sec is 1 on cos. This one doesn't have a one, but CSC is 1 on sine, and cot is 1 on tan. Cool. And we use these one-on variations so often we've given them their own special letter abbreviations, which is slightly frustrating, but they behave exactly the same, and anytime you see them, you can just write it as one-on, one-on, one-on. They come up very rarely. All right, so function derivative of tan x. This is the only sort of proof you need to know. I'm just going to drop the screen a second. So, important place to start is to remember that tan x is equal to sine x over cosine of x. As soon as you've got sine x over cosine of x, you've got the quotient rule set up. This is u, this is v. So u, v, u dash, v dash. If u is sine x, sine is simple, its derivative is cos x. If v is cos x, it's difficult, so it's minus sine x. Then putting it into the quotient rule, dy on dx is u dash v, so cos x v cos x, minus v dash minus sine x sine x over v squared, so cos x squared. So we can tidy this a little. Dy dx is, when you have them multiplied by each other, you can write it as cos squared, and the way we write cos squared is like that. My plus, note the double negative, sine squared x over cos squared x. Alright, now, some of you may recognize cos squared x plus sine squared x from trig properties of last year, but that is probably the most famous trig identity. That is equal to 1, coming from the unit circle. So dy dx equals 1 over cos squared x. So if we take tan, the derivative of it is 1 on cos squared. Note, the chain rule still applies. So if you are deriving sine of a function of x, that goes to cosine of that function multiplied by the derivative of whatever was inside the sine rule. Same with cos, same with tan. So, examples. There are quite a few examples. I'll try to go through them quickly. Alright, anything connected with plus or minus you can deal with separately. So very simply, dy dx on this case, dy dx is going to go, well, sine is simple, so 3 cos x. Cos goes to minus sine, so it's going to make a plus 4 sine x. Leave it there. Alright, here, there are two functions of x multiplied by each other in there. So we're thinking product rule. Everything we've learned previously still applies. U equals x3, v equals tan x. U dash is 3x squared, v dash is 1 on cos squared x. Dy dx is u dash v, so 3x squared tan x, plus, now when you multiply 1 on cos squared x by x to the power of 3, you get not just a giant 3, you get x to the power of 3 over cos squared x. And you would leave it there. No need to simplify further. Alright, here we've got a function of x. Function of x divided by another function of x. So we're using quotient rule. Again, just with trig, but quotient rule. Alright, so u, not meant to do that. U is x, v is 1 plus sine x. U dash, because it's difficult, is minus sine x. V dash, the 1 derives to 0, sine is just cos x. Then, dy dx is u dash v minus v dash u over v squared. This is u dash, so minus sine x times v, bracket 1 plus sine x, minus v dash cos x over v squared, which is 1 plus sine x squared. Now I'm not going to simplify it, but if I was, I would multiply that in, and I would recognize that on the top, I'm probably going to be able to pull out a 1 somehow because I'll have a sine squared and a cos squared. And that will simplify the top considerably, but we can leave it there. I think that's our last 2 examples. I've changed my mind, don't want to do this one, so we're going to do a new example. What if we just had y equals sine of 4x squared plus 7x? Alright, if we're going to do this, it's chain rule. This is the inner function, so u. If we let that equal u, then, and we say this is y equals sine u, dy dx is the derivative of sine u, so cos u multiplied by u dash. That's that chain rule coming out on the end. And when you're doing these, you don't actually have to write these intermediate steps. I'm just sort of showing it for clarity here. Y dx equals cos of 4x squared plus 7x multiplied by the derivative of that inner, and it has to go in brackets here, so 8x plus 7. Right. So that's showing the chain function. Here, another one of the chain function. So tan bracket sine x would look like this. dy on dx is 1 over cos squared of sine x multiplied by the derivative of the inner, so cos x. And you can rewrite that with that on top of the fraction, but other than that, that's as far as you go. Alright, and that is all. Thank you for listening. Please bring these notes to class and get ready to have some fun with trig functions. See you on Tuesday.